Blackboard site, these are data sheets. Data sheets are very important to understand. And okay, let's do that. On Blackboard, these are in the data sheet section. So these are all the data sheets that we'll be looking at, hopefully. Right now we're looking at, so here's the 914. This is the one that y'all are actually doing the lab on. The one that we're going to use most often is the 1 in 40,000 series of diodes. These are the ones that we're going to be doing all our tests on. Each one of these data sheet books up here will. So the 1 in 4,000 series. So actually, the data sheet covers the 4001 through the 4007. And you should have one of these data sheets in your book, so you'll need to look in there and find it. So y'all on the 4001 through the 4007 data sheet, you'll find it in y'all's in the data sheet book. So what symmetric means, I don't know, but these are rectifier diodes, right? You understand? And then this is the data sheet. So just about every data sheet you run into semiconductors has two different tables in it. Number one, it has what it calls the maximum rating table. The maximum rating table, these are specifications that if we operate it within this limit, they guarantee it will not be damaged. And then we have the electrical characteristics. This is where we normally want to operate the thing at. Y'all understand that? Y'all see the two tables? So you notice these things start off with up here on the reverse breakover. So this is what your book calls VIP, peak inverse voltage. Like I've never understand that because you won't find that inside data sheets. And data sheets is going to be one of these right here, VRRM, which is the peak reverse, peak repetitive reverse breakover voltage. And this is the only 3 lines in this data sheet that's set apart. So the only difference between a 4001 and a 4007 is how much reverse bias it can handle before it breaks over. So these are the breakover voltages. So 1 in 4001, it could handle up to 50 volts continuously without breaking over. Where the 4007 can handle what? Up to 1,000. Now this is repetitive. Non-repetitive, which is usually for a half cycle, then the 1 in 4001 can handle up to 60 volts, and then the 1 in 4007 can handle up to 1,200 volts. So that would be in a half-wave rectifier. In a full-wave rectifier, we'd be looking at the top. On a half-wave rectifier, we'd be looking at the bottom, right? I mean, the second one. Does that make sense? Everybody okay? The third one would be what your meter would measure. So these are all peak voltages. So these are repetitive peak voltages. You would have to see this on an oscilloscope. But what they've also done is given you that value in RMS. Everybody okay there? That makes sense. No, we're looking at we're starting on the maximum rating table because that's where things vary. Everything after that, everything after the maximum rating table is the same from the 4001 all the way up to the 4007. So basically, the only thing that varies between these series is how much reverse breakover voltage they can handle. After that, everything's the same. So that means I could replace a 4001 with a 4007, but I cannot replace a 4007 with a 4001. You know what I'm saying? So you can use a diode that's better, but you can't use a diode that's worse, right? You understand? So when the engineer designed that, if they used the 4007, they did it so it would block 1,000 volts. So if you put a 4001 in there, odds are you're going to wipe it out, right? You understand? So I can put a diode in there that's got better specs, but I should never put one in there that's got worse specs, right? You understand that? Now, once we get over the breakover voltage, we see how much current this guy can handle. This guy can handle up to 1 amp at 60 hertz and at 75 degrees Celsius. I'll say centigrade, guys. That's the way I learned it, but they officially changed the name to Celsius. So that's probably what you know. Unfortunately, over here in the United States, we don't use Celsius. We use what? Fahrenheit. So you need to know how to convert those. Anybody know how to convert to Fahrenheit? Well, we know freezing on the Celsius scale is 0, but freezing on the Fahrenheit scale is 32, which is weird. On the Celsius scale, 100 is boiling. On the Fahrenheit scale, it's 212. So if you looked at the difference between the marks between freezing and boiling, for every nine marks of the Fahrenheit scale, there's 5 marks on the centigrade scale. That means we're either going to use 9/5 or we're going to use 5/9. So when I go to Fahrenheit is bigger, so I'm going to use 9/5. When I'm going to Celsius, I'll use 5/9, and some of y'all know the number. First of all, we have to set them even, so we're either going to subtract 32 or add 32 to set 0 at the same point. So what I'm going to do is I'm going to take 75, that's what they're saying, and then I'm going to multiply that. I'm going to open up parentheses. We're going big to little, so I'm going to put 9 divided by 5, which is going to be 1.8, and none people know that. Then I'm going to equal that, and I'm going to add 32 to it. So I mean, this guy could go all the way up to, that didn't work out right. Thank you. Because that didn't work out right, because I know it's like 175 degrees, or 160 something. So 75 times 1.8 plus 32. So this guy could go up to 167 degrees Fahrenheit and still be able to maintain 167 degrees. Now that's ambient temperature. What is ambient temperature? It is the temperature that is surrounding the device. So the ambient temperature inside my computer would be more than the ambient temperature out here, right? You understand? That's why we have to. So ambient means the surrounding. So it's exactly where this thing's operating in. So if we're out in Alabama, we had a scale down at Columbiana that I was working on, a digital scale, and it would go crazy. And then when we got down there, when we went down there, everything would be working right. And what was happening was they would use it during the day, and it would go crazy because they had the scale inside this little shed. And in Alabama during the summertime, there was no air conditioning or even fans blowing in there, and it would get up to well over 100 degrees, and the scale would go crazy. We would go out at 8 o'clock in the morning when we went out on calls, and we would get there and everything would be and we couldn't find anything wrong with the scale. And that was the reason. They had no watt in the building. They had no cooling in the building. Okay. Well, the problem, it was another little problem, but it was because of heat. So this is why we have to cool semiconductors, right? You understand? So this computer's got a fan on it. I feel it running right now. You know, the higher the power, and if you get a real nice desktop, that really operates at some super high speeds, then you're going to have all kinds of cooling in there. You over there on those robots, you hear these fans running inside those robot controllers all the time, just to try to keep what? Try to keep those semiconductors cool. So, but non-repetitive, this guy could handle up to what? For one cycle, it could handle up to what? 30 amps, which is important. Are we okay? Then we're not going to look at the junction temperature. We can operate this thing anywhere between 65 degrees, minus 65 degrees centigrade, up to, now this is not operate. What is this? I'm sorry, it is operating and storage junction temperature. We can operate this anywhere between that range right there, which is really cold up to really hot. So this is a pretty good semiconductor. Now the next one, this is where we should operate it at. So it says the maximum instantaneous forward voltage drop. This is if we're having it conducting 1 amp, at 25 degrees centigrade, and you're going to find out 25 degrees centigrade is used a lot in semiconductors, and that's around 75 degrees. The average voltage drop on this thing could be anywhere between what? This is operating at the maximum current, right? At the maximum room temperature. This guy is going to drop anywhere between 930 millivolts all the way up to 1.1 volt. So that 0.7 of a volt we're talking about is just an approximation, right? You understand that? The maximum full cycle voltage drop at 75, 1 amp would be what? 800 millivolts. So this guy should be pretty good. Okay? Are you okay? Any questions on that? Here we get into the leakage current. Leakage current, when this thing operates at 25 degrees centigrade, it should be somewhere between 50 nanoamps and 10 microamps. By the way, data sheets don't use legal engineer notation because what they're trying to do is use 1 unit over here, right? You understand that? In here, you are required to use legal engineer notation. So 50 nanoamps up to what? 50 microamps up to what? I'm sorry, this is microamps. 50 nanoamps to what? 10 microamps. Everybody okay? Okay. And then the full cycle average leakage current could be all the way up to 30 microamps. And this is at 75 degrees centigrade. So we're going to see, you can see right off the bat, leakage current is controlled by temperature. So they only give us 2 readings, which is 25 degrees centigrade and 100 degrees centigrade, Celsius, I'm sorry. But it varies 40 microamps between that range. Are we okay? All this makes sense? Yes, no? Data books up here, huh? We're going over the data sheets for the 1N4001 diode. That was recorded, by the way. So here's the data books up here in this box right here. No, you got to come up and get them. So we're going to be using these on tests, and there's questions relative to this data sheet right here on the test. So if y'all got any questions about it, you need to ask now. No, it's just going to put, it's either going to give you maximum or minimums. So it's not going to be dealing with temperature. So if we talk about the maximum we will ever see a reverse current with this thing without damage, then the answer would be 50 microamps. Right? That makes sense? So we don't give temperature. So you don't have to do any conversions, but you're going to have to do that, right? And we'll say, like, what's the maximum average current this thing can handle? Average rectifier forward current for single phase would be 1 amp, right? Does that make sense? So I'm not going to let you're not going to have to go 75 degrees Celsius or anything like that. That's not on the test. That's a good question. What's that? It's a 1. You just can't hardly see the dot right there. These are all 1 amp diodes. That would be nice. 10 amp would be a pretty good sized diode. These are little tiny black ones. You just can't hardly see that little dot right there. I can see it on mine pretty easy. So that's a good question too. And notice there's a space, and this is one thing you need to look at. So notice how close these numbers are together right here and how spaced these are right there. So you know there's got to be something in the center right there. So that's a good question too. Because a lot of times, the more time we look at these, you know, these little dots have a tendency to disappear. So that's a good question too. Any more? What do you mean the electrical? Yeah, because that's that's where you're supposed to operate this thing. Maximum ratings, guys, this is maximum ratings. What maximum ratings does, it says, okay, if you operate it between this range, it's not going to be damaged. The electrical characteristics is telling us what we should see if we're actually operating it the way it's supposed to be operated. That makes sense? In fact, in digital, the maximum rating tables in digital, the device might not even work. It just means it won't be damaged, right? Does that make sense? So these are a little different. Any more questions? So like I said, in your data sheets, in your book, they're going to call this PIV. But in the data sheets, like I said, I've never seen it called PIV. But it's pretty obvious when they say peak, reverse, right? Peak, repetitive, reverse voltage. So that means this guy is reverse biased. If you exceed these, then the device could be what? Damaged, yeah. Does it guarantee it'll work? No. For diodes, it does. But for a lot of solid state devices, it don't mean it will work. It means it will what? It won't be damaged. Are we okay? Yes, no? You guess. So if you don't understand something, you need to ask. People say, well, I don't know what to ask, right? But yeah, on the maximum side. But it can actually be anywhere within these levels right here. So that's what you got to look when it says like maximums or minimums. That's the way it'll be worded on the test. No, that's not type. This is typical. Yes, excuse me. Yeah. So typical, this is what we should expect to measure, right? You understand? But it could go as high as what? 10, yeah. So typical, so we should expect at 100 degrees centigrade or Celsius, we should expect 1 microamp, but it could be up to 50 and it would still be considered within its range of operation. So that's a really good question because most people see that as type, but a lot of these data sheets is going to show typical, and these are measurements that you expect to get, right? So that's a good question. Any more? Huh? So this shows what we should expect when it's in operation. This says, okay, this is what we get, and it won't be damaged, right? Right? That makes sense. Okay, any more? Well, on data sheet, we're going to be looking at a lot of data sheets this semester, and some of them show minimum, maximum, and typical. This data sheet here don't show minimum; it just shows maximum and typical. So that's a good question too. But when we get into bipolar transistors, it's going to have a minimum and maximum, and then it's going to have. Sometimes they don't have a typical either, and that's what gets you into the little. So we okay? We used to get the. I need to find my Motorola book. We used to have to look these things up in data books, and these data books were good gracious. The Motorola book we have probably is about 5 inches thick. We don't do that anymore. If you want a data sheet, what can you do? Yeah, yeah, or you just come in here and you type in the number, and it's mostly available. Don't pay for these things. A lot of places do this, and they want you to pay for them. I guarantee you can find them for free. So just type in the part number, come up in your search bar, 1N 4001, type that in, and you'll come up here and you'll get all types of things. And what you can say 4001 PDF is what usually what we look for. So shows you images. So this is really good to know because you'll get into devices out there. Now remember, if you got a part that's bad, you don't want to replace it with something that's less. You usually can replace it with something that's better, right? You understand? So like I said, we could replace a 4001 with a 4007, but I wouldn't replace a 4007 with a 4001. So because of the breakover voltage, right? Okay, guys, let's go to lab.